Okay. So this morning, oh, there we go. Okay, so this morning I'm going to give my advanced topics talk, and what this is really the rest of the story from yesterday. So yesterday I showed you an example of how to use Artemis to fit some data to get all the way to something like an answer in an XAPS analysis problem. But in fact, I skipped over a lot of the really important topics. So probably the most important thing that I sort of paved over yesterday was at the end of the talk, at the end of the presentation of Artemis, I put in a few more paths, those ones that are drawn there on the board. I put in a few more paths, did some parameters, hit the fit button again, and got a fit, and I said, well, this is a good fit. And then I kind of stopped the lecture. But what I didn't really talk about in any great detail yesterday was how you decide what a good fit is. Or another way to phrase that is you could spend hours and hours poking at the buttons in Artemis, tweaking the parameters, doing this and that, playing with your data, and how do you know when to stop? Right? You can always do something a little bit more. It's a nonlinear fit. It's not like an auto race where there's a guy waving the black and white flag at the end of the race to tell you when to stop driving. So part of the story is to understand enough about the statistical model behind the fitting software to be able to interpret the results that you have at any stage of the analysis, and then hopefully to know when to stop. And so the first part of the talk, and probably the most important part of the talk then, is the beginning where we talk about the statistics. And then the rest of the talk is an explanation of the various kinds of tricks and tools that are built into the data analysis software that will get you to the end, that will provide you with the tools that you need to effectively and cleverly and creatively provide a model for your data and hopefully interpret something out of your data. Actually, this is worth mentioning. I've shown a few of these talks and I haven't mentioned this. So I pointing out the copyright page, just that these things are really like, when I tell you to download them from my GitHub page, they're yours to use. If any of this information is useful to you in another presentation you make or in anything you come up with, this material is not mine. This material is ours, and these are the conditions under which you can use it. Basically, it just means that you have to attribute any ideas or ways of expressing things that you get from me, but these are materials that everybody can use, and, that's good. All right, same acknowledgments as the other day. Matt, my longtime collaborator, and my teachers, John and Ed, everything I'm going to present here is, thanks to those folks, and of course, thanks to all of you who use my software and help improve the state of things. So this isn't the introductory talk, but hopefully it's not the scary talk. It's the talk that will, as I said, explain all of the underpinnings of how the data analysis software works. So you'll see in the talk that basically I'm going to assume that you've seen everything we've seen in the last 2 days. For those of you who are coming to this for the first time, this will possibly be some challenging material, but I think it will be of great use if you continue to move forward in XAPS to have seen all of this stuff, so that after you have a bit more exposure to XAPS, you can come back to this material and think about it again. After I talk about the statistical model behind the fitting and how to interpret the statistics that Artemis presents to you at the end of the fit, we're going to talk about all of the different categories of tricks that the software uses to help you understand and interpret your data in the best possible way. And so we're going to talk about all sorts of useful things, including how to use more than one theft calculation to understand your data, how to use more than one data set. So measure an ensemble of data all at once is a pretty useful thing. and also to talk about how you actually build constraints between the parameters and build interesting and physically significant fitting models. And all of these things are in the software, and we'll talk about them one after the other. But first we need to talk about statistics, because this is really the fundamental question. As I said, you have to know how to evaluate the quality of your fit and the quality of your results. You have to know not only how to start fitting, but you have to know how to stop fitting. Now, this talk starts off much the same way that my first talk yesterday started off. Sometimes you have beautiful data, and sometimes you don't. Here's the example of beautiful data. It's that one scan on the germanium antimonide alloy on silica. And you get this, if you set up this isn't one scan, this is a merge of 5 scans, as you will. If you set up the experiment properly, you can measure beautiful data even on a nominally challenging sample like a really thin film, and you get beautiful data in K, and you do a Fourier transform, and you get all kinds of peaks that are available for analyzing in Artemis. And if you use a Fourier transform that goes over this range, which is 3 to 13, and you try to interpret the data in R space over a certain range, and the range that I show is from 1.7 to 4.7 angstroms, then there's this thing called the Nyquist criterion that is a result of signal processing. So the first use of, or early use of Fourier analysis was the processing and understanding of radio signals, where the amount of information that could be packed into a signal and transmitted, it turns out has something to do with the band pass in the space of, in signal processing, you have a time sequence of an EM signal, and you do a Fourier transform to the frequency space. In excess, the analog to the time signal is, of course, the signal in photoelectron wave number, and the analog to the frequency spectrum is this Fourier transform into real space. But the amount of information that can be contained in a signal like this has something to do with the width of the band in the original space and the width of the band in the Fourier transform space, multiplied by a constant that, if you go and read up on Fourier analysis, the constant turns out to be 2 over pi. So the amount of information that's contained in a signal of which you examine this portion is 2 delta k delta r over pi, which for a large k range and a large range in r turns out in this case to be 19. And that is an upper bound on the amount of information that you could possibly extract from a signal like this. It may be, for reasons we'll talk about in a few slides, that you can't actually get 19 pieces of information out of this signal, but you certainly will not be able to extract with statistical significance more than that number of parameters when you go and fit your data. So this is an upper bound of what you could hope to learn from a signal that looks like that. At the other end, you have something that isn't exactly beautiful, and this is the not beautiful example I gave yesterday also, where I spent 22 hours measuring 42 scans of a fairly low concentration of a solution containing mercury, and at the end of the day, literally at the end of the day, because I spent 22 hours on it, I ended up with this much usable signal in K space, much, much less than in the last slide, and a couple of clear, well-resolved above-the-noise peaks in R. And when you apply the Nyquist criterion, you get all of 8. So there's a lot less information that I could hope to get out of data like this. And the point of this talk, and really the point of learning how to use Artemis well, is not to learn how to analyze these data. That's relatively easy because they're beautiful data and you can extract a lot of information from them. The point here is to learn how to use data that we, more commonly see in real research problems, data that is, frankly, not so great. And how do you get useful information and make useful scientific progress with data that looks like that? So we first have to understand what this Nyquist criterion is and what it means. So what I gave you before was the formula, but what are the conceptual underpinnings behind that formula? Well, that formula applies if the following are all true. The signal is ideally packed, and the error in the fitting parameters is normally distributed, and we understand and can enumerate all of the sources of error in the measurement, and we know the theoretical line shape of the data. If all of those things are true, then the number of independent points in data, the number of parameters you can extract from the data is is approximately 2 delta k delta r over pi. So, to understand the validity of this near equation, we have to examine these 4 points. So let's think about those and see how many of those 4 points are actually true in a typical x-axis measurement. So I'm just going to tell you the answer. The answer is none of them are true in an x-axis measurement. So our signal is not ideally packed. The meaning of ideally packed in this context is that your signal is a sum of pure sine waves, and that's demonstrably not true. There's the Debye-Waller-like term that damps the sine wave. The sine wave is multiplied by f of k, which is something that has structure. So our signal is not ideally packed. It's almost ideally packed. It's basically the sum of sine waves, but it's not the sum of pure sine waves. The error in the fitting parameters is normally distributed. Well, that might be, or it might not be. It kind of depends upon how you parameterize the problem. And even if you do the simplest possible thing and use the terms in the x-axis equation as the parameters of the fit, it's not clear that something that has a complicated dependence in the fit, like delta E or sigma squared, really will have its errors normally distributed. So point number 2 may or may not be true, but can't be relied upon. Understand and enumerate all the sources of error. That's actually possible, I suppose, if your beamline scientist goes to extraordinary lengths to measure the linearity of all parts of the beamline from the source all the way down to the hutch, but most of us don't do that. I certainly don't do that at my beamline. And in any case, to really enumerate all the sources of error, you also have to characterize your sample extraordinarily well. You have to know to what extent your sample can be said to be homogeneous, and most of us, with a few possible counterexamples, don't know about the homogeneity of our samples. It's possible that you might have a sample in liquid contained in a vessel that you know does not have any effective surface tension to change its thickness. But beyond that, none of us really know that our samples are truly homogeneous or don't suffer from any other problem. So we probably don't really know, and we certainly haven't enumerated all the sources of our error. And as for the theoretical line shape, well, what I mean by that is that in, for example, a Mossbauer experiment, you pretty much know that the shape of your spectrum is a line with some Gaussians that point down. And so that's an example of a case where you know to a pretty good level what the theoretical line shape of your experiment is. In our case, we are using the Feth calculation to come up with F and delta in the x-axis equation over there. And Feth makes approximations. So we don't know the theoretical line shape of our measurement because we're using Feth, and Feth makes approximations. So not a single criterion is met. The end result of that is that the amount of information in an x-axis spectrum is less than 2 delta k delta r. So Artemis reports this upper bound, but you need to be mindful of the fact that that it's just an upper bound. So I've just spent several minutes explaining what a disaster that the statistical underpinnings of the software are. Does that mean that it's time to close the book and go home and find something else to do? Well, No, I don't think so, because although this equation doesn't hold true, there's still value that can be brought out of applying simple Gaussian statistics to a problem that suffers from all four of those problems. So before I get into that, I need to define what the terms are in the statistical model, and these are the terms that are reported in the log file at the end of the fit. So chi-squared is the actual fitting metric. This is the quantity that is minimized during the fit. That is, what I mean by that is that you somehow set up the parameters of your fit and start turning the crank. IFEFIT starts with your initial guesses for all the parameters, evaluates the x-axis equation for all the paths, and evaluates chi-squared, which is the sum over all of the data points of the squares of the differences of the real and imaginary parts of the Fourier transforms of the data in the theory. So you Fourier transform the data, you sum up and Fourier transform the theory, and you evaluate the difference in the real part and square it, evaluate the difference in the imaginary part and square it, add all of those things up, normalize by the appropriate numbers, and this quantity is minimized. So the fit stops when chi-squared stops getting smaller. So it adjusts the guess parameters until chi-squared stops getting smaller. So this is the fitting metric. The somewhat more useful quantity than the fitting metric is what's called the reduced chi-squared, which is the value of chi-squared normalized by the amount of freedom in the fit. And the amount of freedom in the fit is simply the number of unused information points. So we evaluate that NIDP thing, subtract the number of variables that were actually floating in the fit, and whatever the freedom is, that normalizes reduced chi-squared. And as you see, this number is the number that we spend most of our time looking at when we evaluate the statistical quality of a fit. One oddball part of this equation is the epsilon, and the epsilon is the measurement uncertainty, and there will be a sequence of slides about determining measurement uncertainty in a little bit. This is central to understanding what's going on with epsilon is central to understanding what's going on with the software, so we're going to talk about that at some length. Finally, there's a parameter that's called the R factor, which is not as generally useful a statistical parameter as reduced chi-squared for reasons that I'll talk about shortly. It has this big long formula, and the way that I like to think about the R factor is that it's a measure of percentage misfit. Or another way to say that is it's a numerical measure of the extent to which the red line overplots the blue line when Artemis plots a fit, the results of a fit. Now, you can go and get a book on Gaussian statistics, on measurement statistics. There's an error analysis in the physical sciences by a guy named Bebbington, which has gone through a million printings over the years. It's just this really great book. It should probably be on every scientist's desk. And he derives Gaussian statistics and explains that a good fit is one for which, this is supposed to say chi nu squared equals 1. So the reduced chi-squared of a good fit is 1 in the statistical model in which all these things are derived. So in Gaussian statistics, there is a criterion for what a good fit is. And a good fit is one for which the misfit measured this way, normalized by the amount of freedom, so this thing, chi nu squared, is 1. And that's what a good fit is. So here's an example of a fit in x-axis. This is just the copper foil that we all have at our beam lines, and measured in transmission. And this one was measured at 10 Kelvin. They're extraordinarily good data that go out all the way above 20 inverse angstroms. And here's a quick little fit I did to the first 2 shells of copper metal. And you can see that in the numerical misfit sense, the R factor is 0.1, 1% misfit. And truly, the red line just falls right on top of the blue line when plotted in R space. If you evaluate NIDP for the parameters that I used in this fit, you get a value of 16 for the number of independent points, and I only used 4 parameters, an S0 squared, an energy shift, and an isotropic expansion coefficient, just like what we used yesterday for iron sulfide, and a little trick for determining all the sigma squares in the problem, where you can relate the sigma squared in an XAPS fit to the Debye temperature, to the behavior of the acoustic phonons in the material. So I have this 4-parameter fit to fit 2 shells to copper metal. These numbers are all quite reasonable. That's approximately the right number for the Debye temperature for copper. That's the right value for the copper lattice constant. That's a reasonable number. That's a reasonable number. We have a really close fit, only 1% misfit. And when we do all the stuff in IFEFIT, we end up with a reduced chi-squared of 228, which is clearly not 1. It's not even approximately 1, except in the furthest, most generous sense of the word approximate. So what's going on? How can we have a fit that is unambiguously, easily, defendably good as this fit and still have a reduced chi-squared of 227? Well, the answer is that we need to talk about this number right here, the epsilon, the measurement uncertainty. Let me tell you how IFEFIT measures the measurement uncertainty. It's a bit hokey. It's the way epsilon is evaluated is actually a little hard to defend, but it's easy to explain. It comes up with a number, and it's what's used in the software. And what we do is we do the Fourier transform of chi of k, and then look at the region out between 15 and 25 in chi of r. The assumption here being that because of the mean free path term, which I don't have written up on the board, but there's a mean free path term in the equation, and the 1 over r, and the effect of sigma squared, all of those things together conspire to mean that you probably don't really have any signal between 15 and 25 inverse angstroms in most real materials. And that is to say that XAPS is a nearsighted local structure measurement. There's just not, the ansatz is that there's just not signal between 15 and 25 inverse angstroms. So anything that does exist between 15 and 25 inverse angstroms must be noise, must be shot noise, because the Fourier transform of white noise is more white noise. So if there's white noise in chi of k, it Fourier transforms to the same level of white noise in chi of r, and that is what we assume to be seen out between 15 and 25. And that is probably true for many things. It's not obviously true for copper metal. If you actually look at the signal from copper metal all the way out there, there really does seem to be some kind of structure that is different from noise. But that's because these are extraordinarily good data. And most data that you measure, and most certainly in the example of the data that I gave that was bad data, there's nothing out here except noise. But this is just a measure of the statistical noise, the shot noise. And that's just never the limiting problem in an XAPS experiment, right? Because what I mean by shot noise is noise on your detectors. And say, take I0 as the most extreme example. The level of noise on I0 is really, really low, because at even a really bad beamline like my beamline, we're still putting 10 to the 9 or 10 to the 10, on a good day I suppose, photons into I0. There's a lot of photons in I0. The level of noise on I0 is really, really low. Noise in an XAPS experiment is dominated by all the other problems. It's dominated by the mistakes that are made by FEF. It's dominated by sample inhomogeneity or nonlinearities in the beamline. Sort of everything else besides shot noise are the limiting things in your ability to better use your data. So this approach of measuring between 15 and 25 is pretty much guaranteed to underestimate the level of uncertainty, of measurement uncertainty in your analysis. What does that mean? Well, if epsilon is underdetermined by the algorithm that IFEFIT uses, then epsilon is much too small of a number, and chi-squared evaluates to much larger than it should have. In the case of the copper metal, you can approximate by how much epsilon was under-evaluated. It was under-evaluated by exactly the level that made reduced chi-squared 227 rather than 1. So that under-approximation of epsilon is really quite significant. In fact, it's orders of magnitude wrong. So, all right, again, is it time to close the book and go home and do something else? Well, no. We can still back our way out of this problem of not properly determining the statistics of the measurement, and here's how it goes. So we just accept that epsilon is never evaluated correctly. We live with that and move on. The result of epsilon always being under-evaluated is that reduced chi-squared is always a number that is between big and enormous. Almost never 1. Once in a blue moon, it will be 1. That means that we can't use chi-squared to interpret the quality of a single fit. That is, you cannot press the fit button once, have a result, and say, I'm done. This is the best fit. This is a good fit. This is statistically good. I'm done. I'm going to go publish now and then go home. You can't do that with a single fit. You can't press the fit button once. But what you can do is use reduced chi-square to compare different fits. So if you change something about the model, if you introduce a constraint between parameters or lift a constraint between parameters, thereby changing the number of guess parameters in the fit, if you add some more paths, if you do something to change the fitting model and then press the fit button again, well, you can use reduced chi-squared to say whether the second fit is better or worse than the previous fit. And that's really the bottom line, is that we can do successive fits, changing the fitting model in some appropriate way, and know whether the change has made forward progress or has moved us backwards. So reduced chi-squared is a very useful statistical parameter, but it's useful in the context of comparing different fitting models. And that turns out to be the whole key to using IFEFIT and Artemis. Now, there's a potential problem with the error bars, because the math that is used to evaluate chi-squared, and therefore to evaluate reduced chi-squared, that same math is used to evaluate the error bars on the parameters. For those who know something about this kind of numerical analysis, in the course of evaluating chi-squared, there's a thing called the covariance matrix that's evaluated at every step. And this matrix has all of the information about the parameters and the correlations between the parameters in it. The error bars turn out to be the diagonal elements of the covariance matrix. Okay, blah, blah, blah. If reduced chi-squared is way too big because epsilon has been determined to be a number that is way too small, the consequence of that is that the diagonal elements of this matrix will also be much too small. So if IFEFIT were to simply report the diagonal elements of the covariance matrix, which is what you're supposed to do in basic Gaussian statistics, the statistical model on which all of this is based, then the error bars would always be extremely too small. In the case of the copper, where we had reasonably sized error bars, they would be too small by the square root of that, which is about 15. So all these uncertainties would be 15 times too small. And that would be really suspicious, because then you would be saying that you could measure these things with a precision that is vastly greater than what is commonly accepted in the literature. Well, and that would be because you would be making the mistake of reporting the unnormalized, whoops, I went too far. you would be making the mistake of reporting the unnormalized uncertainty. So what we do is we assume that the fit that you make is a good fit. Right? That's not to say that it is a good fit. That's something that, as we'll talk about, you have to determine when you're running the fit. But iFEFIT assumes that every fit is a good fit and simply rescales the error bars to the size they would have been had you evaluated epsilon correctly. So, when iFEFIT, when Artemis presents the log file and gives you the values of the parameters with their error bars, the error bars are the right size to report if that's the fit you're going to report in your publication or in your talk. That is, if you determine the fit is a good fit, the error bars reported are scaled by the right amount to be the physically correct 1 sigma error bars. So the bottom line there being that the log file is reliable. So how do we know? So okay. So now I've told you how, like, what the meanings of all the numbers are. How do we actually say that a fit is a good fit? Well, if the current fit is an improvement over the previous fit, you can determine that if chi-squared gets smaller. So you know that you're moving towards a good fit. If you start changing the parameters in some reasonable way and reduce chi-squared just doesn't change, then you've probably gotten to the end of the road, and that's as good as your fit is going to get. You should be suspicious of a fit for which the number of variables is very close to the number of independent points. That is, a fit for which nu is very small. And the reason for that is that when you introduce a number of parameters that's very close to the maximal information content of the data, it's likely that the correlations between the parameters will go up significantly, and that all of the parameters will be very ill-determined. The error bars will probably be very large. In general, it's best to do a fit using as little of the information as possible. That is, to make all of your parameters as robust and strong in the fit as possible. Your variable parameters have to be defensible, and they have to make physical sense. If you get a fit that looks like a beautiful fit in the sense of the red line overplotting the blue line, but you have crazy parameter values, it's probably not a good fit, because the fit has to give you numbers that make physical sense, or you really haven't done something useful. The results should be consistent with other things you know about the sample. If you've done, say, a UV vis experiment to determine something about what kinds of ligands you have in the material, or if you've done some diffraction on a crystal and you know something about the structure of the crystal, or any of these things, and then you do an X-APS experiment and the story is wildly different from other things you know about the material, you either need to reconsider the X-APS analysis, or you need to come up with a way to explain why the X-APS measurement would be wildly different from the other things you've measured on the material. So, the other way to say this is that one never just does X-APS on a sample and then goes to publish. X-APS is usually part of a broader research program. The R factor should be small and the fit should closely overplot the data. Well, that's a redundant statement because a small R factor means the fit overplots the data. But if the R factor isn't small, reduced chi-squared is probably really large, and and none of the rest of these things will be true. So this one sort of follows from all the rest of them. So how do we get a handle on this point about these 2 points about defensible, physically consistent error bars and reasonable results? Well, let me just give you a couple of examples to get you thinking about that. A fitted sigma squared that is not positive definite is troubling, and that's troubling because sigma squared is sigma squared. It can't be negative. It's a real number squared. In the situation where you run the fit and sigma squared comes out to be a negative number or a small number that is not positive definite, that's usually telling you something about a shortcoming of the physical model. That is, you've assumed something about the structure in your material that is not consistent with what you actually measured. And at the end of the day, when you do understand the structure of the thing that you're measuring, you should find that all of your sigma squareds are positive definite numbers. On the other hand, if you get an E0 value that is not positive definite, that's no problem whatsoever, because you just pick some value of E0 in Athena, you have a parameter that lines up the energy grid of the data with the theory, and it is what it is. If you have a number that's consistent with 0 like this, that just says you've made a really good choice of E0 back in Athena. If E0 is a bit more positive than that or a bit more negative than that, that's also just fine. So how you interpret the error bar depends upon what the meaning of the parameter is. And, right, something that you have to be mindful of as you're creating your model. Now there's also all kinds of outside knowledge that we use to understand our x-axis data. Our outside knowledge could be as simple as another x-axis measurement, and the classic example of that is the assumption of chemical transferability of S0 squared, which I talked about with several of you, which is the concept that if you go to the beamline and say you're measuring a palladium catalyst that has, some complicated thing going on, you first make a good measurement of the palladium foil, do the data analysis on the palladium foil for which you know the coordination number in the x-axis experiment, and the amplitude that you would extract from that analysis then you interpret as the S0 squared parameter in the x-axis equation. You could then use that number as a decent approximation of S0 squared in the unknown sample, and thereby use that number to extract coordination number from the unknown sample. So your other measurement might be as simple as another x-axis measurement, but all kinds of other common measurements give you useful and interesting information about the structure of your sample that can guide you in interpreting your x-axis data, and you should use that information. There's of course also common sense. A near neighbor distance is never a half an angstrom, and the nearest neighbor distance is never 4 angstroms. Sigma squareds are never negative because it's a positive definite number. So common sense certainly helps. If you get a number that your common sense tells you is really wacky, then you should trust your common sense. And really anything else that you know. You are the expert in the thing that you're working on. You have a physical or chemical or biological or geological or whatever a logical intuition about what your sample is, and you should bring that to the table when you're doing x-axis analysis. So taking all of that together, mindful of all of that, it's time to start casting the fitting problem the way that it's done in IFEFIT. So all of this is familiar. We talked about it yesterday, and we have it up on the board over there. Here's the x-axis equation. This equation has to be evaluated for every path that's used in the fit. You sum up the paths, have your theoretical chi of k, that is the thing that's compared to your data, and used to evaluate chi-squared from many slides ago. There's a couple of more hidden parameters in here. There's the delta R and the delta E naught. And we use FEF. The FEF calculation is run to evaluate the gray terms, the scattering function, the complex scattering function. FEF also tells us what the mean free path is, and gives us an R naught, or an R effective, for every path in the fit. That is the distance at which the FEF calculation was made. And we somehow, by hook or by crook, have to evaluate the 5 blue terms in the x-axis equation. And here in this box is the bottom line of how Artemis works. In IFEFIT, in Artemis, the terms in blue are not themselves the fitting parameter. They are written in terms of the actual fitting parameters. I'm going to say that several more times before I get to the end of this talk. Here is the flow of events. When you press the big button in the upper corner of Artemis, this is the flow of events that happens. So you have created a set of parameters, some of which are the variables of the fit, the things that will change to determine the fit. Some of them are set parameters. They're just a parameter that's set to a value of a number. Some of them are something called a def parameter that I haven't quite talked about yet, but which we'll get into later on in the talk. And a def parameter is a parameter that is written in terms of a math expression. So it is a parameter that is functionally dependent upon one or more of the guess parameters. So you define a set of parameters. You define a set of path parameters. In the context of Artemis, here you fill in the window, the guess def set window, that table of parameters. Here you fill in the boxes for all of the paths that you include in the fit. So these two things together are what you do to define your fitting model. You use math expressions like alpha times ref, like the little approximations we made for sigma squared for the multiple scattering paths. You use math expressions to relate the parameters of the x-axis equation, the path parameters, the things in green over there, to relate those to the parameters on the guess set def page. When you press the fit button, the path parameters are all evaluated using the current values of all of the guess parameters. The sum is made, the sum is compared to the data, and chi-squared is evaluated. It checks to see if this evaluation of chi-squared is sufficiently different than the previous evaluation of chi-squared. If it's not, if they're the same and the fit is finished, then it reports the errors and it evaluates the uncertainties and reports the errors and writes the log file. If chi-squared is changed, then it uses an algorithm to update the values of all of the guess parameters. It reevaluates all of the parameters that are defined by math expressions in terms of the guess parameters, reevaluates the path parameters, does the sum, computes chi-squared, and goes through this loop until it stops changing, and then it writes the log file. That is what happens when you press the fit button. You create a model, press the fit button, go around this loop, and finally finish. That's Artemis. Okay, so before I start to dive into all of the clever tricks that are available in Artemis, I think I should stop and see if anyone has any statistics questions. Yes?
I have a question, because when you scale the error bars with chi-square...
Reduce chi-squared, but okay, yeah.
You say that the error bars are smaller if your reduced chi-square is bigger.
Yes.
But does that mean I get smaller error bars for a worse fit?
No, maybe. It sounds situational. What it means is that every time you run a fit, and every time that IFFIT reports error bars, it scales them such that if that was the fit you want to run with, those are the right-sized error bars. But whether or not that's the fit you want to run with is something that cannot be determined because of, well, essentially because of the flaws in evaluating epsilon. So it's up to you to determine whether it's a good fit. But if it's a good fit, then the error bars have been scaled to the right level. It's not completely satisfying, but it's within the context of this statistical model, it's impossible to do better because we don't have a way to a posteriori evaluate the uncertainties due to problems at the beamline or the sample or the theory. And it would be possible, so some in the room might understand what I'm about to say. There are other statistical models. For example, you could do your analysis in a Bayesian context. And one of the things that the Bayesian approach allows you to do is to probe the data to understand what, not the sources of, but what the levels of measurement error are in the problem. But, and there's been some work on that, and that's great. It turns out that in practice, you can do less work than that. You can do this, and just be mindful of what the problems are and still come up with like a defensible answer. And it's just a lot simpler to write and maintain a Gaussian program than a Bayesian program. Yes?
On what basis did you choose the formula n formula to calculate the number of random parameters? For what I know, literal represents another two options of this formula by adding either one or two at the end of it.
Yes, I just decided to step out of the debate of whether it's +1 or +2.
Okay,
If you go read, that's why I use the approximately equal.
now I know.
So the formal statement, if you go way back and look at the early signal processing papers, it's +1. My esteemed and thoroughly lovable thesis advisor wrote a paper that suggested that in the context of x-axis it should be +2. In virtually no other ways do I ever disagree with Ed, but I don't agree with him on that. So I think Ed is mistaken, but I'm also just not a big enough guy to really get up and say, no, Ed is wrong, don't listen to Ed. He's more important than I am. So I choose to just get out of the argument and drop the +1, drop the +2, because the truth of the matter is that if you're worried about the +1 or the +2, you are probably trying to fit too many parameters. Because the truth of the matter is that because the signal is not ideally packed, we probably don't really have quite that many parameters. In fact, the people who have done Bayesian analyses of x-axis suggest that the real number is something like 2/3 of delta k delta r plus 1. So if the Bayesian folk who are less sensitive to all of the problems in the statistical model tell us that the number is quite a bit less than delta k delta r, then truly it doesn't matter whether you evaluate delta k delta r plus 1, or delta k delta r plus 2. It just doesn't matter. So I just wrote it down like that.
Yeah. Okay.
Yes?
So say I'm going through my fit and I've defined a variable for the sort of all the parameters s0 squared. I've got to a point where I need more variables. It seems s0 squared is sort of staying roughly the same for each sort of each improvement that I do. Can I then sort of fix that and continue on with the statistics sort of they remain good?
Well, so the answer is either sure, of course, or certainly not, no way. What I mean by that is that it's not that you can or can't fix it. Mechanically in the program, you can always fix it or not fix it. It's just a matter of toggling guess to set. Okay, so as far as running the program, you can do whatever you want. It's up to you at the end of the day to defend what you do. So the way I want to answer that question is to tell you what the consequence of fitting s0 squared is. And the consequence is that you lose the ability to evaluate correlations between s0 squared and the things with which it's highly correlated. So, and that's principally the sigma squareds in the problem. So by fixing s0 squared, you don't quite fix the values of sigma squared in the fit, but you constrain them. And you may or may not be constraining them around their correct values. You may just be constraining them about some numerical minimum in the complicated manifold of the fitting parameters. So you certainly can, and if the situation is, as you say, that every single sample for which you have measured the whatever edge, you keep getting the same value of s0 squared, and you feel confident in fixing it, and you feel confident that you're not unduly biasing other parameters, then by all means do so. But you have to be mindful that you've made a choice that has consequences. And when it comes time to defend your choice, that means that you open yourself up to a certain kind of criticism that you have to be prepared to deflect. So it's like everything else in this kind of numerical analysis. It's just a matter of honesty and reporting what you do. So yes, the answer is sure, go ahead, or certainly not, depending upon what exactly is going on. But that's a great question. All right, so everybody doing okay with sitting and listening to a talk? Should we take a little break, or should I carry on? Carry on seems to be what everyone is saying. Okay. In fact, nobody really said anything, so I'm going to carry on. Okay, so there's a whole bunch of different tricks that we have to help us understand our data and help us deal with all of the other problems that we have in our statistical model. An interesting trick number one is what we used to call a multiple k-weight fit, but which in the current version of Artemis, by default, we just call a fit. So a multiple k-weight fit works like this. So if we look again at the x-apps equation, we notice that not all of the terms in blue have the same relationship with wave number as the other terms. For example, sigma squared is multiplied by k squared, whereas on the other hand, r is multiplied just by k. And if you go through, if you work on the back of an envelope, what a delta E means, delta E is more or less multiplied by 1 over k. And so what I mean by this is that when you evaluate chi squared, and yes, it is ridiculously confusing that chi is both a statistical parameter and the symbol used for the x-apps equation. So, but this thing never gets squared. So anytime I say chi squared, I mean the statistical parameter, and anytime I say chi, I mean this thing. When you evaluate chi squared, if you have a misfit in sigma squared, if you have the wrong value for sigma squared, then that is going to contribute a much larger amount of misfit, contribute much more to the evaluation of chi squared at high k, because then you have a wrong number multiplied by k squared. However, at low k, the wrong value of sigma squared has a much smaller effect on the data. Similarly, delta r, since r is multiplied by k, if it's the wrong number, it contributes more misfit at high k. Contrary-wise, delta E naught, a mistake in the shift to line up the k grids, is a bigger problem at low k. It contributes more misfit at low k than at high k. So if we evaluate chi squared using a k-weight of 3 in the Fourier transform, multiply chi of k by k cubed, we blow up the high k end of the data, and a misfit in sigma squared contributes much more profoundly to chi squared than, for example, S naught squared, which is sort of equally affects the whole range of data. Similarly, if you use k cubed weighting in the evaluation of chi squared, then the wrong value of delta r is a really serious problem because it contributes really significantly to the evaluation of chi squared. On the other hand, if you use a k-weight of 1, that puts a bit more emphasis on getting this number right, because then the signal at high k is quite a bit smaller, and the misfit at low k dominates the evaluation of chi squared. So using a different k-weight puts a different emphasis on the 4 parameters, because the high value of k-weight, in some sense, requires the fit to do a better job of fitting sigma squared and delta r than it does requiring the correct value of delta E naught. And if you use a smaller k-weight, the opposite is true. Well, we really want to evaluate everything well, so what we do is a multiple k-weight fit. And this often is found by people to be a difficult, complicated concept, and it truly couldn't be any simpler. We evaluate chi-squared, and this is the same formula I showed several slides ago. We evaluate this thing using some value of k weighting, and then we evaluate it again using a different value of k weighting, and simply add them all up. And the thing that's minimized is the sum of this term evaluated with different k weights. So when we do a multiple k weight fit, we evaluate the fit with k weight of 1, so that we do a really good job getting E naught correct. And we also evaluate it with a k weight of 3, so that we do a really good job of getting the delta r's and the sigma squareds correct. And we minimize the sum of those things. And that's what a multiple k weight fit. It really is, it's really very simple. But it gives us a better measure of all of our parameters, because it evaluates a thing that is sensitive to each of the parameters, and there's a term in there that then forces each of the parameters to be as good as it can possibly be. So here's an example of that in action. Here's this methyl tin thing that I referred to yesterday, where we have some data that are slightly different depending upon how many chlorines we have in the thing. And if I do a fit with only k weight of 2, we get actually not a bad fit. The red line is pretty much on top of the blue line pretty well. The R factor is really small. But we have some strange values. The amplitude, which should be something around 1, of course, because it's meant to represent sigma, S0 squared. The amplitude came out really, really big, but also the sigma squareds came out really, really big. And you can see that this carbon signal is really, really broad. It's not really a nice, sharp peak function like we expect. So we did this single k-weight fit, and the numbers just didn't come out right. And on top of that, there's a really high correlation between a couple of the parameters. This just isn't all that good of a fit. And the problem is because we're really severely impacting the information limit in the data, where 6 is just too close to 7. And these parameters turn out not to be particularly robust. So we don't make the information problem go away. This is still a somewhat suspect fit using so many variables. However, simply by evaluating chi-squared a little bit differently, by doing this multiple k-weight thing, we just give the fit more to grab onto, and do a good job of simultaneously determining S0 squared, which affects the whole k range sort of equally, and sigma squared, which is very getting that right is very sensitive at the high range. So including the multiple k-weight thing made all 3 of those numbers a lot more reasonable. Now the amplitude is still a little bit strange, but the sigma squareds are much more the kinds of numbers that you expect, and the result of the fit is much more what you expect to see for something like this. So here, by doing nothing to address the constrained information problem, doing nothing more than simply evaluating the fit in the multiple k-weight sense, we do a much better job of making our fitting model a robust fitting model. This would still need some attention paid to it to figure out if everything is quite right, but just doing the multiple k-weight thing really helps. So it used to be that in the old version of Artemis, the default was to do some kind of single k-weight fit, and now the default is to always do a multiple k-weight fit. And you can see that if you have Artemis open in front of you, that on one of the data pages where the fitting k-weight buttons are, they come up by default all ticked on. And the reason for that is that after years of practice, those of us who are at the center of this IFEFIT thing, we just can't come up with a good reason why you should ever want to do a fit other than in the multiple k-weight manner. So that's now the default in Artemis. So suppose that you have a problem like any of the following. Suppose that you have a crystal with multiple inequivalent positions in the unit cell, or you have a metalloprotein with a bunch of different sites for the metal atom to be, or any of these other things. There are all these things where the absorbing atom can be in all kinds of different environments. And the thing that all of these have in common is that you can't run Pfeff once and expect to do all of these things, because there's no way that you can run Pfeff once to get more than one active site in the center in a metalloprotein. In all of these cases, you have to run Pfeff more than once. So how do we deal with that? Well, here's a really simple example, a simple crystal example. The famous high temperature, one of the first high temperature superconductors was this guy, yttrium barium copper oxide. And the thing I want to draw your attention to is that the copper has two inequivalent sites. There are two different kinds of copper in the unit cell for yttrium barium copper oxide. One is in this fourfold planar configuration, and the other is in the middle of a square pyramid. So one of them has 4 neighbors, one of them has 5 neighbors, and site 2 is quite a bit more structurally disordered because it's at the middle of a pyramid rather than at the middle of something more symmetric. So these are really quite different positions. So the only way to make progress on this problem is that you have to run Pfeff once using the first copper site as the absorber. Here, copper 1 was chosen as the absorber. And then you have to run Pfeff a second time with the copper 2 site chosen as the absorber. And then you need to somehow take paths from one Pfeff calculation, paths from the other Pfeff calculation, and include them all into the fit. And in this case, you'd have to do, but you have to do so wisely. Because as you remember yesterday, I said that the reason that we unit normalize our data, did I say that yesterday? Maybe I said that the day before. The reason that we unit normalize our data, or one of the reasons we do so, is because when the theory is run, it generates chi of k of the right size to be compared with unit normalized data. Well, if we run the Pfeff 1 the site 1 calculation, that is calculated assuming that the thing that you're going to measure only has copper atoms in site 1. Similarly, when we run the site 2 calculation, it's scaled to the right size, assuming that you only have data from the second site, but we don't. We have 1/3 of our signal comes from the copper 1 site, and 2/3 of our signal comes from the copper 2 site. So we would have to do something like this. We'd have to guess our sigma squared, our S0 squared parameter, and then instead of just applying that to every one of the paths, we would have to scale them appropriately. So the ones from site 1 would have to be scaled by 1/3, and the ones from site 2 would have to be scaled by 2/3, because 1/3 of the signal in this material comes from site 1, because there's 1 of them, and 2/3 of the material comes from site 2, because there's 2 of them. So when you have one of these multiple absorber site problems, you have to do, there are 2 tricks to solving it. One is you have to run Pfeff more than once, and step 2 is you have to scale them according to the, what's the right word? The relative proportions of the different metal sites, which in this case is 1/3 and 2/3. So here's a more interesting example, and it's the one that I alluded to yesterday in the little discussion about proceeding with non-crystalline materials. We have this uranyl ion adsorbed to biomass, either a uranyl floating in water or attached to a phosphoryl or carboxyl ligand. And we know a bunch of things about this. Uranyls always have 5 or 6 equatorial oxygens. We know that the phosphoryl ligand is monodentate, and we know that the carboxyl ligand is bidentate. Obviously there's no Pfeff input file for that. As I said yesterday, we use this crystalline material to model this portion of the scattering. We use this crystalline material to model this portion of the scattering, and we weight them appropriately. As I said yesterday, everything is explained in this paper, which is a great paper and should be read regardless of whether you look at this kind of material. There's instructional value in here for everyone. I went through this yesterday, so I won't in great detail today, but we know that in this mess, there's a little structural unit that is what we need, and in this mess, there's a little structural unit that is what we need. And when we run the Pfeff calculation and import the pads into the fit, the evaluation of the fit goes like this. So to construct the theory, for every Pfeff calculation that we do, and this is a sum over all of the Pfeff calculations that we use to do the fit, we evaluate chi for every path in each Pfeff calculation and sum them all up. So we sum up all the paths from one Pfeff calculation, sum up all the paths from the other Pfeff calculation, sum those two sums together, and when we evaluate chi squared and evaluate the theory part of chi squared, we're taking the sum over all paths from all Pfeff calculations. So again, the multiple Pfeff calculation thing is really very simple. You're just, instead of taking all your theory from one Pfeff calculation, you take it from several different places, add them up, and that's the fit. It's pretty simple. The last big trick is the multiple data set trick. And this could be any number of things. It could be a bunch of different temperature data in a cryostat or a furnace. You could be doing something in a pressure cell at multiple pressures. You could have all sorts of things, including multiple edges of the same material. And it's useful in some situations to refine such ensembles of data together. And that's pretty simple. So earlier in the talk, I showed you the top part of this, which was that obviously good fit copper metal, which was just evaluated with a sigma squared and E naught, lattice expansion coefficient, and a sigma squared determined from the Dubai temperature. So we have data at two different temperatures here that we can co-refine together, but we can't use the same lattice expansion coefficient at the different temperatures because the lattice expansion coefficient should be temperature dependent. So if we assume that the lattice expansion is just simply linear in temperature, which isn't a horrible approximation, it's probably not quite right, but it's not a horrible approximation. And certainly if you have two temperatures, you can make a line between 2 points regardless of what the functional form is. So as long as I have two temperatures, this is fine. So I just make a line where the temperature is something I know for each sample, and now M and B, the slope and the offset, are parameters in the fit. So I doubled the amount of information by co-refining the data, but I only added one more parameter. And as long as I'm willing to stay within this linear approximation, I can add any additional temperatures and better determine this set of parameters with more and more data without ever introducing more parameters. And so you throw more information at the problem without throwing more parameters. Presumably, if the model is sensible and the data are all good, your parameters will be better and better determined the more data you use in a situation like this. So multiple data set fitting is a really valuable thing. And again, it's conceptually very simple. You evaluate chi squared for every data included in the fit. You add up all of those chi squareds, and it's the sum of those chi squareds that are minimized when you run the fit. So again, the multiple data set fit is a trivial extension of the evaluation of chi squared. Here's an example. Where we left this off last time, we had improved the methyl tin fit by including multiple K weights that helped make the fitting parameters more robust. Here we are going to throw more data at the problem by co-refining these two groups. The only change we need to make is that we need to remember that in the dimethyl tin there are 2 carbons and 2 chlorines, and in the trimethyl tin there are 3 carbons and 1 chlorine. But other than that, we assert that the tin-chlorine bond is the same in both of those materials, and the tin-carbon bond is the same in both of those materials. That's a reasonable assumption for the first guess. It's something that you might need to explore in further analysis. But as a first guess, it's a reasonable assumption. And so we assume that the bond lengths and the sigma squares are going to be the same in either dimethyl or trimethyl-tin. And we import both data sets, parameterize them the same with the exception of doing the coordination numbers correctly. And we fit both data sets at the same time and come up with this result, where the difference between this, which is the contribution from, so this one and this one are the contributions from the chlorine, from the carbon, and the yellow one and the purple one are the contributions from the chlorine, and they use the same sigma squared and the same delta R for both data sets, but here it's one carbon and 3 chlorine, and here it's 2 carbon and 2 chlorine. Except for that, we use the rest of the parameters the same. We have twice as much information to determine the same set of parameters that we were having trouble measuring before, and we end up with a reasonably good fit. Another example I won't go through would be something like europium titanate, where you can go and measure the titanium K edge and the europium L edge and consider analyzing them both at the same time. There are a couple of things that they share in common. All the delta R's are determined by a single parameter, the lattice constant, and in each case you'll have a scattering path that is europium titanium, or titanium europium, and the sigma squared measured from either side should be the same. So there are some common parameters between the data. And in this case, I had data for over a range of temperatures. So I have multiple temperatures. I have 2 edges. I have to do 2 Pfeff calculations, one for the titanium center, one for the europium center. So I get to throw a lot of tricks at this problem. I get to do multiple Pfeff calculations and multiple data set fitting, and you can actually go and really nail down that problem. So, okay, we're almost at the end here. Here's just refresh you of what the flow through the calculation is. And now it's time to talk about this corner of the flow chart a little bit more. And this is really where Artemis and IFEFIT get all their great stuff. So we've already talked about this slide already, the problem where we have 5 parameters that have to be determined for every path. But even for beautiful data, we have a limited number of paths. So at 20 independent points and 5 parameters, what happens if we have to include 5 or more paths in the fit? Well, obviously we're doomed because 5 times 5 is bigger than that. But of course we're not. And the reason that we're not is because the parameters of the x-axis equation are not themselves the parameters of the fit. The parameters of the x-axis equation are written in terms of the parameters of the fit. So we talked about S0 and E0 yesterday. So if you're doing a relatively simple fit with a single element and a single Pfeff calculation, then S0 squared and E0 are the same parameter for all paths. So it's not the problem from the previous page. We get to constrain S0 squared for every path to be the same, and we get to constrain E0 for every path to be the same. In the case of the copper, we got to do the alpha times ref trick to constrain all the delta R's together because copper is a cubic metal. And in the case of copper, we can use the correlated Debye model to relate the sigma squareds to the Debye temperature of copper. And that further reduces the number of parameters by constraining path parameters to be, not to be the same, but to behave according to a certain function. In this case, delta R is not the parameter of the fit. Delta R is written in terms of the parameter of the fit, and delta R for every path is then calculated from a single guess parameter, in this case, this magical ref parameter. But those are all pretty boring. Let's look at a more interesting problem. Let's go back to this thing. How does Shelley actually solve this problem? Well, if you start looking at this, so the original problem is to figure out in the real system how many phosphoroligands there were and how many carboxyligands there were. So the phosphoroligand is monodentate. So the number of phosphorus atoms, oh, wait, I need to tell you one other thing. That these equatorial oxygen atoms aren't necessarily the same length. The oxygen atom that is monodentate with the phosphorus atom is shorter by a considerable amount, by 0.05, somewhere between 0.05 and 0.1. So this oxygen atom is at a considerably shorter distance than this oxygen atom. Enough shorter that you can start to tell them apart in a sort of typical X-APS analysis. So if you have a phosphorus atom, you have a short oxygen atom. If there are, say, 3 phosphoryl ligands, there are 3 phosphorus scatterers, and that means there are 3 oxygen atoms at the shorter distance. So the number of P's is equal to the number of shorts. Similarly, the carbon atom is bidentate, so if there is a carbon scatterer, there are 2 longer oxygen scatterers. So the number of carbon atoms is equal to half the number of long oxygen atoms. And in general, these uranyl ions have 5 or 6 equatorial oxygens. When I looked at this data, and when Shelley looked at this data, there seemed pretty good evidence that the species we were seeing in those data were all had 6 equatorial oxygens. So at the beginning of the analysis, I simply asserted that there would be 6 of these equatorial oxygens. So the number of short oxygens plus the number of long oxygens equals 6. So we don't actually have 4 distinct parameters. In fact, we only have 1 parameter, right? If we assert that there are 6 oxygens in total, then the only variable is, say, the number of short atoms. That's floated in the fit, and all 3 of these other numbers can then be evaluated based on the current value of n short. How is that done? Well, it's done like this. We set n equatorial to be 6, so I'm asserting that there are 6. I guess the number of shorts, and then I def these other interesting parameters to be functionally dependent upon n short in the way I described on the last page. And then later on in the path parameters where we evaluate the X-APS equation, we use these as the coordination numbers in the determination of each of those paths. So here's a really interesting example of building interesting constraints among parameters. What do I mean by constraints? Well, instead of having independent coordination numbers for all those various oxygen, phosphorus, and carbon scatterers, they're not independent. They're all constrained to be related in this way. Now, I asserted by setting n equatorial to 6, I'm asserting that there are 6 equatorial oxygens. It's very easy to lift that constraint simply by changing the set to a guess. And I don't have to go and edit a lot of stuff. I just, up on the guess def set page, I simply change n underscore eq from a set to a guess, and that lifts the constraint. Setting that constraint or lifting the constraint, that's the kind of thing I was talking about, that you can compare reduced chi-squareds for different models. If you run the fit with this guessed and then run it with that number set, reduced chi-squared will change somehow. If one of them is significantly lower, that's the better fit. That's what I mean by comparing reduced chi-squared, and that's what I mean by lifting and setting a constraint. Yeah, I'm going to skip over this last part of the problem and just point out a few things. That the multiple k-weight fitting happens down here, and you'll see by default that all 3 of these buttons typically come up ticked when you start up Artemis. And they're not to be confused with the k-weight buttons from up here that just tell you what k-weight will be used for the fitting. For plotting the data, for visualizing the data. The multiple Feth calculations is also really simple. Here you see that I have imported the Feth calculation for the copper 1 site. Here's the copper 2 site. Some of the items in this list are from the copper 1 site. Some of them are from the copper 2 site. And when I finally go to start evaluating what's supposed to go in this block, I have to remember to put in the 1/3 and the 2/3 thing. But multiple theft calculations is super simple. You just import all the theft calculations you need, and then drag and drop the paths that you want from the calculation onto the data. With the caveat that there's an upper limit to how many paths you can possibly use in a fit. But that's a pretty big number for most people. Multiple data sets is similarly really easy. However, there's two things you might want to do with a second data set. You can simply change what data set you're looking at. So you could, for example, analyze your data at 10 Kelvin and then say, okay, now I want to apply this fitting model to my data at 100 Kelvin. And then you would just simply, in the data window, say, replace this chi of k. That will open up the dialog for importing data from an Athena project file and simply replace the data with the new data. But you could also import new data, in which case you'll just start to get a stack of data sets in this part of the main window, and that works like this. Here's what I had when I did the methyl tin multiple data set fit. I had 2 items in this list and 2 data pages. One of them is the dimethyl tin, and one of them is the monomethyl tin, and I just parameterize them accordingly. Constraints are fairly simply specified. Here are all the constraints that I had a few slides ago when I showed you that clever relationship between the number of short and long oxygens and the number of carbons and phosphoruses. It all just looks like this in the guest F set window. And this is the part of the talk that I skipped over for now. And yeah, okay. And now that's all the tricks. So, in principle, you know just about everything I know now. So go do all those things and measure great data. Well, okay, you do that in the opposite order. Go measure great data over at the beamlines over there, and then go do all of those tricks. And then, ideally, I will start getting really excellent papers to review instead of papers that I have to send back for further consideration. So do all that stuff. And that's everything about fitting. Any questions before I fall over? Yes?
Yeah, unlike the multiple data set, for multiple calculation, I guess there will be more parameters that we need to play with. And then if I am interested in delta R more than, say, the sigma square, can we actually refine, can we actually fit first the delta R, and then, because we have a limit of independent, and then, or we can guess, like, if we have the experiment at very low temperature, can we guess that that parameter should be really low number or something like that?
Okay, well, there were 2 questions in there, actually. Possibly 3. So as for limited data and trying to determine first delta R and then sigma squared, my answer to that is the same thing as my answer to that fellow's question. When you fix a number and measure another number, there's consequence to that. And if, say, you have 7 independent points and you want to determine 10 numbers, and you say, okay, I'm going to fit 5 of them and determine the other 5. Now I'm going to fix those 5 and determine the other 5. Well, you're trying to cheat, right? That clearly, you clearly aren't doing something clever there. You really are trying to determine 10 numbers from 7 independent points. So if you want to make, so you can do any constraints that you want. I'm not looking over your shoulder telling you what buttons to push when you're running Artemis. So of course you can do that. The question is, at the end of the day, do you end up with defensible parameters? And, in an extreme case like that, the answer is probably not. So you have to be mindful of the fact that the thing that you're trying to do has to end up with numbers that you can defend. And you have to be mindful of the fact that that kind of fix this, guess that, guess this, fit this, guess that, that kind of strategy has the same problem that I explained to that guy, which is that you are just completely ignoring certain correlations between parameters that might actually be quite significant. Now, as for how many parameters you have to introduce in a multiple theft calculation versus a multiple data set approach to analyzing your data, it really all kind of depends. In the case of copper at multiple temperatures, I added a lot more data, but barely any more parameters because each data set was so closely related to all of the other ones. They only changed by temperature. But in the case of the europium titanate, there are a smaller number of parameters that are in common between the data sets. And in the case of doing a multiple edge multi-data set fit, you often end up having to introduce quite a large number of parameters when you add the new data set. But what you hope is that there are enough parameters in common between the data sets that it is an advantage to do the multiple data set fitting. And there was a third question in there, but I can't remember what it was.
The low temperature, would that be possible that the sigma square can be lower?
Oh, yes, right. And actually, that's a good question. So yes, of course, sigma squared is going to be lower at lower temperature. And when you get to the stage where you have some fitting results and you have to decide if they're physically believable, if you can defend them, if they're physically reasonable, that's the kind of knowledge that you can assert. That if you have a sequence of temperature data and the sigma squareds are all increasing the way sigma squared should, then you've probably got a pretty good fitting model. But if you have a sequence of fitting data and the sigma squareds are doing this, that's probably pretty weird, and you probably need to think about what you did to interpret that whole ensemble of data. That is, an ensemble of data has to make sense as an ensemble of data. But certainly sigma squared should be smaller at lower temperature. That's absolutely how sigma squared behaves. And it's a good way of dealing with the correlation between S naught squared and sigma squared, because S naught squared should not be temperature dependent. So if you do a multiple data set fit, S naught squared is something that's the same for all temperatures, and sigma squared is something that has to change for the temperatures. They might change in an algorithmic way, or you might have independent parameters for some reason, but they should change. Yes?
When you do actually the fits with a lot of parameters, how sure can you be that the program is not going to stuck in some local minimum rather than the global minimum of the function? Really, how robust this fitting procedure is?
Not very, I guess. It's just Levenberg-Marquardt minimization. So it does happen on occasion that if you try a different starting value for some parameter, you end up in a very different place. You see that on occasion. But in my experience, it's less common than you might think, because although the signal's not ideally packed, it really is just a bunch of damped sine waves. And so the surface of that multivariate manifold is not quite so complicated in practice as it could be in a general steepest descent fitting problem. That is, most steepest descents take you to the same place, but there are counterexamples. Particularly if you start with really ridiculous values. I mean, if you choose 37 as your first guess for one of your E naughts, then you'll certainly end up in the wrong place. But if you choose 0 or 1 or minus 1, you'll probably end up in the same place. Is that a sufficient answer?
I guess it really very depends on how the function looks like and how the surface looks like. And if it's smooth enough, then I guess.
Yes, and the truth is, it's actually a really valid point, because the evil, the dark other side of Ifefet and Artemis, which have this great feature that you get to write all these cool math expressions and make interesting constraints between parameters and evaluate the path parameters using interesting math expressions. The dark side of that is that you can turn a relatively smooth, multivariate manifold that has all the steepest descents going to the same place. You can turn that into something incredibly complicated. So that is a pitfall of the software. And if you're concerned about that being a pitfall, we don't have an automated way to check yet, although I can think of ways to implement that. You simply have to try, you have to identify which parameters you think might be suspect there and try some different starting points. So we sort of push that responsibility off on the user.